Assalamualaikum and hello. My name is Nur Atira Anis binti Muhammad Saminin and my metro number is 2210922206. I am a student of Bachelor of Electrical Engineering with honor. Now I want to present about my final year project. The title is Design and Development of a Small-Scale Lightning Impulse Voltage Generator. Project was developed based on a three main objective. The first objective is to design a small-scale lightning impulse voltage generator using PC software and hardware. The second objective is to simulate the impulse voltage generator and analyze its performance using PC software. The third objective is to fabricate a hardware prototype and compare its output with the simulation result. However, for the purpose of the presentation, I will be focusing on objective 2, which involves simulating the system and evaluating the effect of component variation of the impulse waveform using PSIM software. This project applied a simulation-based approach using PSIM software. Theoretical value of resistance 1 and resistance 2 were first calculated, then tested in simulations. The waveform produced was analyzed and compared to the standard 1.250 microsecond impulse. By adjusting the resistor value, change in waveform behavior were observed. PSIM was selected as the main tool due to its efficiency, accuracy, and ability to easily modify component value for analysis. PSIM is selected for this project because it's basically designed for high voltage and power circuit simulations. It can accurately generate 1.2 and 50 microsecond lightning input waveform and allow easy adjustment of key components such as capacitor 1, resistor 1, capacitor 2, and resistor 2. The interface is user-friendly with a drag and drop system that simplifies circuit buildings. It also provides fast simulation result and real-time waveform display, making it high efficient for testing and performance analysis. In this simulation, I demonstrate the behavior of an impulse voltage generator circuit using different resistor value. In the first circuit, a capacitor C1 rated at 4.7 nanofarad is charged to 12 kilowatt. When the switch closed, the energy is released through a series resistor R1 and then through a parallel combination of resistor R2 and capacitor C2. This generates an impulse voltage measure at the output. The waveform depends on resistor 1 and resistor value, which affect rise time and decay. In the second setup, I compare four configurations with different R1 and R2 value. This allows us to observe how varied resistance change the peak output and the waveform shape. The smaller R1 result in a faster discharge, while higher R2 gives a slower voltage decay across capacitance 2. This experiment helped in optimizing component for high voltage impulse testing. This simulation successfully produced an impulse waveform with a peak voltage of 7.669 kV, a rise time of 1.13 microseconds, and a tail time of 50.02 microseconds. This value closely matched the standard lightning, which is 1.2 and 50 microseconds. Although the peak voltage is slightly lower than the nominal 10 kV, the results still demonstrate that the circuit design and simulation method are valid and effective. Additional simulation we conduct to study the effect of charging resistor 1 and resistor value. The results show that reducing resistor 1 lead to a shorter rise time, while increasing resistor 2 resulting is a longer tail time. These findings are consistent with theoretical expectation, where resistor 1 control the charging part that affect the waveform rising edge, and resistor 2 influence the discharging part that control the falling edge. This analysis confirms that waveform characteristics can be found through component variation and highlight the effectiveness of PSIM in studying parameter sensitivity. While PSIM is a reliable simulation tool, it does have some limitations. It uses simplified model for certain nonlinear components like spark gap, which may not fully represent real-world behavior such as arc discharge. Additionally, PSIM cannot simulate physical effects like heat, component damage, or insulation breakdown, and it does not support hardware-in-the-loop integrations. Despite this limitation, PSIM remains highly effective for waveform simulation and component analysis, especially in pre-hardware development stage. In conclusion, this project successfully achieved Objective 2 through simulation using PSIM software. The input voltage waveform generated was close to 1.2 and 50 microsecond standard, and key parameters such as rise time and tail time were within acceptable range. The variation of resistor 1 and resistor 2 value validate the theoretical design, and PSIM proved to be a reliable tool for analyzing waveform behavior. Overall, this simulation served as a safe and efficient step before moving on to the hardware implementations.